Okay, now we will solve this problem number 7.5, which is basically fugacity calculation in liquid phase. And we have two questions, one at lower pressure and the other one is at higher pressure. So what is the fugacity of pure liquid N-butane at 260 Kelvin at the following pressures? Part A is 1 bar and part B is 200 bar. So you may assume the density of liquid butane 0.579 gram per cubic centimeter is independent of pressure. That means it does not change with pressure. Now the data we have, like for example, first we will solve part A. So part A first we will solve, which is at 1 bar. So part A is 1 bar. So 1 bar. So 1 bar pressure, and we need to calculate fugacity of liquid at this condition. Now the formula, or for this case, first I think we can get the data. So the data is temperature is 260 Kelvin, which is given. Density is, which is this one, density rho, denoted by rho, that is 0.579 gram per cubic centimeter. That's the density. So we need to calculate fugacity of liquid at 1 bar and then at 200 bar. So the formula for calculating fugacity of liquid is fugacity of liquid is equal to fugacity coefficient saturation pressure exponent integral from saturation pressure to given pressure, specific volume, universal gas constant T for temperature, pressure dP, this term. So basically this is the formula for fugacity calculation in liquid phase. Remember, in this formula, this red highlighted part is different from the rest of the equation. So this red part is called Poynting, I think it's yes, it's Poynting correction factor. I think this should be here in this slide. So Poynting correction factor. So this is Poynting correction factor. And if you see the slide again, so basically if you can see this, So this is the correlation for Fugacity calculation. This one. And you can see that this is after solving the integral. And this term on your this part from exponent to these things, this is called Poynting correction factor. And if you see this graph, if I can magnify this a little bit, if you see this graph, basically on your x-axis you have pressure, along y-axis you have Poynting factor. And if you can see that if pressure is low, the Poynting factor is close to 1. So mean from 0 to 100, if pressure is from 0 to 100, so like for example you're here, the Poynting factor is not changing significantly because these plots are for Poynting factor. So these are different Poynting factor lines at different temperatures, right? So basically, as you can see that at lower pressure, Poynting factor is not changing much. But as you go in like at higher pressures like this, so you can see that the Poynting factor value changes significantly at higher pressure. So that's why the rule is that if pressure is less than 100 bar, PC mean Poynting correction factor, or this term, whole term, which I talked about. So for low pressures less than 100 bar, Poynting correction factor is considered as 1. Mean at low pressure, Fugacity of liquid is exactly equal to saturation pressure, because this term will become 1 and this is normally 1 as well. So as a result, Fugacity of liquid is exactly equal to saturation pressure. So this is basically the logic and background and theory behind this thing. Now, as you know that now that this Poynting correction factor or the pressure for part A is 1 bar, that means for this case Poynting correction factor is approximately equal to 1, and Fugacity coefficient for this case, because pressure is low, and that is equal to 1 as well. So as a result, you can see that Fugacity of liquid is equal to saturation pressure, right? Now we know this Fugacity of liquid is equal to saturation pressure, which is also equal to Antony's equation, right? So which is Antony's equation is basically exp exponent A minus B over C plus T. So this is Antony's equation, right? Which is used for calculating saturation pressure. Now, from where we can get these A, B, and C values? Temperature is given. Now, we need to check appendix A.1, I guess. So if you go to your book, this is critical physical property data, appendix A. This is Antony's equation, as you can see that here. So this is basically Antony's equation, and this is the equation. And when you take the antilog, so this becomes exp. A, B, C, temperature is in Kelvin. And these are the values of A, B, and C. And this is the temperature range for which it is applicable. Now we have N-butane, So we need to look for N-butane here. So this is N-butane, right? And the molecular weight is 74.11. So please note down this. So molecular weight, sorry, it's N-butanol, sorry for this, not N-butane. We're looking for N-butane, which is this one. Please note down molecular weight 58.122. So this is molecular weight. Now go further. This is value of A, 9.0580. This is value of B, which is 2154.90. And this is value of C, which is negative 34.42. So we got A, B, and C values. The temperature range for which this thing is valid is minimum 195 and maximum 290, but our temperature is 260, so that means this data is valid for our case. So after noting down these values, so I can write these A, B, and C values from that appendix, which is 9.0580, B is 2154.9, and C is negative 34.42. Now we can put these values in this formula, which is EXP. A is 9.0580 minus B is 2154.9 over minus C is minus 34.42 plus temperature is in Kelvin, which is 260, which is correct. So we can put these values here. Now we can solve this. Use your calculator, and fugacity of liquid is equal to exactly saturation pressure. After solving this Antony's equation, so you will get an answer approximately close to 0.610 bar. So this is basically fugacity of liquid at pressure of 1 bar. So this is the answer for part A. Okay, now part B is pressure of 200 bar. Now this is a bit different scenario, because if you remember, we said in this case, if you see, the pointing factor is equal to 1 if pressure is less than 100 bar. But if pressure is 100 or above, then that means we need to calculate this part of the equation, we need to solve this equation itself. Otherwise we don't need to solve, because it's close to 1, so we don't need to solve this. But if pressure is greater than 100 bar, which is the case in part B, then in that case we need to solve this whole equation, like we need to calculate specific volume, RT, everything as well, and integral as well. Now we can solve this thing again using the same formula. So basically, again we can say that fugacity of liquid is saturation pressure, which is close to 1 again. Pi sat we have calculated from part A. EXP and integral Saturation pressure, we already know. Pressure is 200 bar. Specific volume over R is universal gas constant. Temperature is given, and this is dP. So this is the formula, again exactly similar. Now the temperature we already know, which is 260 Kelvin. Saturation pressure is, now I can put the data here again for these things. So data here, data. So temperature is 260 Kelvin. Specific, coefficients, Fugacity coefficient is again 1. Saturation pressure we have calculated from previous part, which is 0.610 bar. Now specific volume. Specific volume is what? That is cubic meters per kilogram. So if we use this, that is equal to molecular weight over density. We will get answer as cubic meters per mole, right? So basically this is the specific volume, right? So molecular weight in this case is, as you noted down previously, so molecular weight was 58.123 kilogram per mole, right? Sorry, gram per mole. Gram per mole. So basically density is 0.579 gram per cubic meters, which is a bit tricky. So the density is 0.579 gram per cubic meters cube. Okay, now what we can do is we can convert this density first. Into kilogram per cubic meters. So for example, this is 0.79 gram. So 0.579 gram over cubic meters, 1000 gram into 1 kilogram, and oops, so basically, and 100 centimeter equal to 1 meter. So we can take the cube on both sides. So then it will become the same thing, right? Now you can see that the density as a result will be something like, so as a result gram will be cancelled with gram, cubic meters will be cancelled with cubic meters like here, so we will get as kilogram per cubic meter. So basically this is how it look like. So what will be the answer as a result? So we will get 579. So we will get 579 kilogram per cubic meters. Now specific volume which we need to use is molecular weight over density, because density is in kilogram but our molecular weight is in gram, so we need to modify this as well. So let's put this again. So that is 58.123 gram per mole divided by density is 579 kilogram per cubic meter. So what we can do is we can do some more conversions. So we can say 1000 gram is equal to 1 kilogram, right? So basically this will be the conversion factor. So gram will be cancelled with gram and kilogram will be cancelled with kilogram, and as a result we will get the specific volume in terms of cubic meters per mole, because if you see, gram will be cancelled with gram, kilogram will be cancelled with kilogram, and the specific volume will be equal to 1 into 10 to raise power minus 4 approximately cubic meters per mole. Now we got these values, and R is a universal gas constant, T is temperature. Now we can just put the values in this formula, which is fugacity of liquid. Fugacity coefficient is 1, saturation pressure is 0.610 bar, exp. So this is 610, P is 200. Specific volume we have just calculated, which is 1 into 10 to raise power minus 4. R is 8.314 multiplied by 260 Kelvin. So basically this is how dP, right? But remember, pressure should be in Pascal. So basically PI sat is 0.610 bar is equal to multiplied by 10 to raise power 5 Pascal. And similarly, this pressure is, which is 200 bar, that is equal to 200 multiplied by 10 to raise power 5 Pascal, because 1 bar is equal to 10 to raise power 5 Pascal. So basically, because this pressure is in bar, and at the bottom we have kilojoule over kilomole Kelvin. So basically we want some cancellation here. So that's why we did all these conversions. So fugacity of liquid becomes 0.610 exp we can solve this as 1 is to 10 to raise power minus 4 from 200 5 Pascal minus 610 into 10 to raise power 5 Pascal pressure over 8.314 into 260 Kelvin. So this is basically the thing, right? So units will cancel out. All the units in this thing will cancel out. I will show you in a minute how they are cancel out. But once you solve this thing, this calculation like this, so you will be able to finalize the answer, which is approximately, so fugacity of liquid you will calculate as a result of approximately 1.53 bar. So this is basically fugacity of liquid at 200 bar. So this is clearly an indication that same liquid, everything looks same, temperature same, but fugacity at 1 bar is 0.61 and fugacity at 200 bar is 1.53. You can see the difference. So this is how it works. So how the pressure is affecting. Now coming back to this unit conversion, for example, so unit conversion here, in this case, how these units are cancelled out. So I can explain this. So basically 1 into 10 to the raised power 4 is what is the unit for specific? It's cubic meters per mole. So basically this is cubic meters. Oops, that's not a good idea. So basically specific volume is cubic meters per mole. Then we have Pascal for this pressure and this pressure, which is Pascal, and Pascal is equal to Newton over meter square over, I think this is kilomole, and this is kilomole as well. Okay, now R is 8.314 kilojoule over kilomole Kelvin, and temperature is Kelvin, right? So now we can cancel Kelvin with Kelvin, kilomole with kilomole, 2 meters with 2 meters here. So we got as a result of this, we got Newton meter, which is joule, and kilojoule. I think that there should be some more unit conversions. Let me double check what they have done. I think cubic meters, okay, it's joule per mole. Sorry for this, it's joule per mole. So basically joule per mole here, so joule per mole, not kilomole. So this is not kilomole, this is not kilomole. I can do this again. So basically this is joule over mole, Newton per meter square, divided by joule over mole Kelvin and Kelvin. So Kelvin is cancelled with Kelvin, mole is cancelled with mole. Newton meter becomes joule, and that joule will be cancelled with joule. So as a result, we will have nothing except the unit here, which is bar. So that's why you will get this unit of bar in the end. So this is basically the solution for problem number 7.5, 750, I guess. So I hope this question is clear to you guys. And this is a very important question, so please look into this carefully. Thank you.